Good morning, everybody. This is Nicolas Zabara speaking. We continue our lectures on statistical computing and machine learning. The lecture today is a continuation of an earlier lecture on Bayesian regression and variable selection. So we will talk more about variable selection and using Gibbs sampling at the second half of the lecture today. So the topics that we will cover today, we will proceed with more an informative prior model, so we will discuss the Jeffreys prior and also an uninformative version of this Zellner's G prior that we saw in the earlier lecture, and then we will start moving in defining this variable selection problem and see how we can handle it both in a Bayesian setting and also using Monte Carlo type of approaches, in particularly Gibbs sampling. All right, so let me review some of the things that we will need from the earlier lecture in case you have not heard of that lecture. So remember, we're looking for linear regression problems. Beta are the regression parameters, and what you see there is our likelihood model that is a Gaussian. The design matrix is X. You remember X involves all the input information we have in our training data set. So every row is one training data point. The first column is all ones to account for the bias term, and every other column corresponds to a particular input dimension. So the design matrix is of dimensions n times k plus 1. So we have k input variables, so plus the bias that gives us the k plus 1, and we take that the noise here sigma square is unknown. Okay, and I gave you various expressions for the likelihood model that somehow we're going to use them today, but all of those expressions are derived by this Gaussian model that we have seen throughout this course. All right, so let me proceed and talk a little bit about what we have seen in the context of conjugate priors. So this is our standard normal inverse gamma conjugate prior. So given sigma squared, the prior on beta was a Gaussian. So remember, tilde of beta is the prior mean. And then we had this covariance matrix being sigma squared m inverse, where m is a k plus 1 times k plus 1 positive definite symmetric matrix. And then we started our discussion by taking sigma squared to follow an inverse gamma distribution. Okay, so this was our first prior model based completely on conjugate analysis, and based on this model we derived all the posteriors and marginal posteriors. We derived the Bayes factors, HPD regions, the marginal likelihood, etc., etc. So that's the first model, and then we discuss about the Zellner's G prior, that is sort of a particular form of the model we just saw. And this Zellner's G prior, first we use an improper Jeffreys prior for sigma square rather than using an inverse gamma distribution. And the distribution of beta given sigma square is of course again a Gaussian, with tilde of beta being the prior mean, but notice now that matrix M that I had before takes a very specific structure, which is X transpose X. In addition, I have a scale parameter C that sort of can be tuned to define how confident I am on this prior. Now, regretfully, all of these prior models that we use, when we use them in practice, we notice, for example, that this Zellner's informative G prior, somehow even when we push C to very high values, still there was an effect on the predictions, and particularly on the bias term, both mean and variance, but also, on the noise sigma square. So this model, even when you push it to the uninformative limit, it was still an informative prior model, so somehow it will not be appropriate when we don't have really any prior knowledge to base upon. So we will need to talk about uninformative models in the lecture today. All right, so let me start with first the Jeffreys prior, and I am going to give you directly what the form is. Basically, the joint prior on beta and sigma squared is going to be 1 over sigma squared. And we have seen this in discussions on prior models before. In essence, what we have is we have a flat prior on the joint of beta and log of sigma squared. And I indicate this prior with the superscript j, just to remind us that this is the Jeffreys prior. So if we take our standard likelihood model, and you remember I am writing the likelihood model as all of these terms here. If you remember, I had expanded the exponential inside the likelihood model in 2 terms by adding and subtracting from beta the MLE estimate of beta. So beta hat is the MLE estimate of beta, and this is my S squared term, the way that I had defined it earlier. So it is the square error between the training responses y and the regression estimate, if you like, x times beta hat, okay, where for beta I use the MLE estimate for beta. And then of course I have my Jeffreys prior 1 over sigma squared, and if I combine terms, they look like this. Now I am not going to repeat all the ideas and calculations we have done before, but if you look at this joint distribution of beta and sigma squared, you can keep sigma squared constant and derive a distribution of beta given sigma squared. So that will be a conditional posterior distribution. Also, you can integrate beta out and derive the marginal posterior on sigma squared, and of course using that you can derive the marginal posterior for beta as well. So let me give you some of those results. The distribution on sigma squared, the posterior on sigma squared, is an inverse gamma distribution with these parameters a and b that you see here. And the distribution, the posterior of beta given sigma squared, turns out to be a Gaussian with a mean, the MLE estimate, and a variance that is sigma squared x transpose x inverse. So immediately, if you want to find the Bayes estimate for sigma squared, you can look at the generic formulas. You know that the mean of the inverse gamma distribution is beta over alpha minus 1. So immediately you can see that the Bayes estimate for sigma squared is s squared divided by n minus k minus 3. And you can see that this estimate is large. So you get a very high variance as your Bayes estimate. So this is a more pessimistic calculation, more pessimistic estimate than what we have seen in the earlier models, which is to be expected because we use an uninformed prior. All right, so we have the posterior distribution for sigma squared, and we have the posterior of beta given sigma squared. So we can take this, multiply it with the posterior of sigma squared, and that will allow us to compute the marginal posterior of beta. And indeed, I can do this calculation, and you can anticipate that, as we have seen in the earlier lecture, the marginal posterior of beta turns out to be a student t distribution. Of course, the dimensionality is k plus 1, that's the dimensionality of beta. The degrees of freedom are n minus k minus 1. The mean is theta, and this covariance matrix is sigma, and you see the exact values that are coming out once you do this integration. So if you want, again, the Bayes estimate for beta, it turns out simply to be the MLE estimate, so that's very convenient. And what is very interesting here, if you look at the distribution of each of the parameters beta I, it turns out to be similar to what we derived in a frequentist setting very early on in the previous lecture, which means that the HPD regions coincide with the frequentist confidence intervals. So actually I will give you in this slide a review of what we had seen for the distribution of beta I minus beta I hat. And these are the frequentist confidence intervals, and they turn out to be the same as the HPD intervals that we get from our Bayesian analysis. However, note, and I mentioned this earlier, these high probability density regions and the confidence intervals that you get in a frequentist setting, they have completely different meanings. So they look the same, the results, but the meaning, of course, is very different. Okay, so here are some of the HPD intervals using the analysis that using this Jeffreys prior, and these are the 95% HPD intervals for each of the parameters using this formula that you see on the bottom here. And again, this is the formula that I have used for the analysis. What I want to emphasize here is, you remember when we use the frequentist confidence intervals, we look at them and we said, you know what, let's see if 0 is contained in that interval, and then if 0 was contained in that interval, then we said there is evidence for the hypothesis H0 that particular parameter beta I, let's say for example, if I look in here, then there was evidence that beta 3 is equal to 0. So that effectively we do not need beta 3 times x3 to be part of our regression model. Unfortunately, you will not be able to do this with HPD regions. Whatever we said in the frequentist setting is basically not quite right in the context of Bayesian analysis. Now, what I wanted to mention also is, if you try to duplicate these results coming from chapter 3 of the Bayesian core textbook, note that somehow the confidence number, the probability that is being referred in the Bayesian core book is not quite right. Okay, so the chapter 3 refers to 90% HPD intervals, when really what is posted is 95%. Okay, so let's continue now with another prior, and I'm going to go back to this Zellner's G prior and try to define some uninformed version of that. So if you remember, in the Zellner's G prior, we had that parameter, that scale parameter C, and we said we were hoping when we push C to very high values that somehow we may be able to get an uninformed prior, but did not really work very well. There was an effect of C in the predictions that we were getting. So what I'm going to do is, I'm going to start first by limiting my discussion to the case of a posterior a prior mean being equal to 0, and then what I'm going to make is I'm going to take this scale parameter C in this Zellner's G prior and make it a random variable, and I'm going to make it a uniform random variable, where the idea here is that, let's say that C takes specific values over the integer set, right? So some integer values. And so the prior that I'm going to put on C is 1 over C. Okay? That's the more general form for this prior. So what I'm going to do is, I am going in deriving posterior for the parameters beta and sigma square, I am going to have to integrate C out. And I indicate here that the posterior of beta and sigma square is basically the posterior that C is given. This is basically what we derived earlier when we worked on the Zellner G prior. There we did not explicitly put C. The implication was that C was already a parameter of the model, but now I am writing it explicitly to indicate that this is the posterior given C. Okay, but this result is exactly what we had in the earlier lecture when we discussed about the Zellner G prior. So what I have is, I have this posterior condition on C times now the posterior on C, and I write the posterior on C as the marginal likelihood given C times the prior divided by this normalization factor. And my prior here is 1 over C, and if I don't bother about the normalization factor, and if I change the integral to a summation over C, and I mentioned before, we're going to take that C takes integer values, we get that this posterior of beta and sigma square is given by this summation, where again, what is different from before is now that we take C to be a random variable with this prior, and once I perform the summation, there is no any more C coming anywhere in the model. So the anticipation, of course, will be that if I do the summation on C, somehow the previous effects we had where there was significant influence by the choice of C on my predictions now will be eliminated. But obviously this is a little bit more complicated. Not only we have to compute this summation for all the C's, but also we have to compute this marginal likelihood for every C. Now, remember that this marginal likelihood in essence was computed before using the Zellner G prior, and we did not indicate this dependence on C, but it was obvious. So really we do have this quantity available, and you will see it shortly coming up in the follow-up slide. Alright, so that's again the same equation for the posterior beta and sigma squared with C integrated out. And here is the expression for the marginal likelihood that we had before. And we mentioned that we will take the prior mean to be equal to 0. So actually I can simplify this equation the way that you see in the bottom of the slide. And right now I have what I need to compute the posterior of beta and sigma squared. So that's the joint posterior. Now, if you remember, when we discussed about the Zellner G prior, I had derived the marginal posterior of beta, right? We had derived the marginal posterior of beta. There was no indication of the dependence of C because it was obvious. So I'm going to now put it there explicitly. So if you look at the previous formulas, the marginal posterior of beta given C was a student t distribution with the particular details that you see in this equation. This formula again was derived in the previous lecture, so please you can visit the video and the PDF to review the derivations of this equation. Okay, so this again was the marginal posterior of beta given a particular value of C. Alright, and of course we can plug in the prior mean to be equal to 0 to simplify. And now the question is, can I get the expectation and the variance of this beta, of the posterior of beta, without actually having to do too much calculations? So can I integrate basically C out without having to do the integration analytically? So let me see what we can do, and this is a trick we used before. Looking at this equation on the top, if you condition beta on the parameter C, you know what the mean is, right? And actually you know what the variance is from the student t distribution. So what you can do is you can use the formulas for the calculation using this iterative expectation formula, and the same thing for the variance. So for example, I can write the mean of the marginal of beta. This is the posterior, but there is no C here, right? So this is my Bayes estimate for beta. I can write this as the expectation with respect to the parameter C of the expectation of beta given C. All right? So first I'm conditioning on C. I am taking the expectation of this with respect to beta, and once I am done, then I take the expectation with respect to C. Now the expectation of beta given C is given by this nice formula, and of course again the curly of beta, this tilde of beta is 0 in our model. So this is the expectation of beta given C. And then what I need to do is I need to take an expectation of all the terms that involve C. So the beta hat, the MLE estimate, goes outside. And then what I have is I have C over C plus 1 times the posterior of C, and I write it this as an anormalized posterior divided by this summation to normalize it. Okay? And you remember the posterior of C, as I indicated before, is the marginal likelihood, which we know what it is, times the prior, which is 1 over C, and the normalization factor looks like that. And the idea here is that we can actually perform this summation without any difficulties, both of those summations. So this is the Bayes estimate for beta. We have integrated C out, right, quite easily. And can we do the same, can we do the same thing for the variance? Yes, and I will show you this momentarily. But before I do that, let me remind you that when we worked on the Zellner's G prior, and again, that case was for a fixed C, we derived the marginal posterior of sigma squared being an inverse gamma distribution. So we had an estimate for the posterior mean of sigma squared, which looks like this, right? So if you remember, for an inverse gamma, the mean is this parameter beta divided by a minus 1. And of course, you're going to put tilde of beta in our model equal to 0. And so eventually, this is what you get for the Bayes estimate for sigma squared. Okay? And now what you will need to do is you will need to integrate C out, and the idea again is the same as I did in the derivation for the Bayes estimate for beta. So what we need to do is multiply this with the posterior of C, which is the likelihood times the prior divided by the normalization factor, and that's the Bayes estimate for sigma squared. Okay? And again, the idea here is that we can compute this normalization factor in the denominator and of course the numerator as well. Now, can we do these things, for example, and compute the variance of beta where C has been integrated out? The answer is, of course, we can. So the variance of beta, of the posterior of beta, is the expectation with respect to C of the variance of beta where C is given, plus the variance with respect to C of the expectation of beta where C is given. Okay? Now, if I start with this term, we know what the expectation of beta is given C is this term with tilde of beta equal to 0, so I plug it in there. And then I have the variance. The first term, I have the expectation with respect to C of the variance of beta with respect to C, which can be derived basically from this term. And I remind you, this is not exactly the variance of the student t distribution. You have to multiply it with the degrees of freedom divided by the degrees of freedom over 2, and that's how this term n minus 2 is coming here. But if you plug in this variance given C, and if you plug in the expectation given C, you get this, all right? So now you are looking carefully, and let's see what we have here. We're going to have to calculate the expectation of this with respect to C, and here we're going to have to calculate the variance of this with respect to C. So if I concentrate on this term, you can see here what I have is I have C over C plus 1 minus the expectation of that, right? That's, again, I'm going to be using the posterior of C to do these expectations, and then square of all of these things times, again, the posterior of C divided by a normalization factor. And because I had a beta hat here, this will come out as a beta hat times beta hat transpose, okay? And then you're going to do the same thing. You're going to have to calculate the expectation of of all of these C terms, okay? You can actually see what happens here, right? If you pay attention to details, I notice here this C has disappeared, and it has disappeared because when I take expectations with respect to the posterior, I'm going to have the marginal likelihood times the prior, which is C minus 1, and this C will cancel out, so only this C plus 1 and this C plus 1 remain there. Again, so we can compute not only the expectation of beta, but also the variance of beta with C completely integrated out. And again, this is the formula that I had before for this marginal likelihood, right? So we had in our previous lecture, we had defined the marginal likelihood given a C. Now, if you multiply this with a prior, the integrals become summations effectively, you have something like that. And because of the shape of the student t distribution, you can actually guarantee that this particular summation exists. Okay, so let me start giving you some results. This is using the Zellner's non-informative G prior. So the C has been integrated out in this model. These are the Bayes estimates for the parameters. This is the computed variance. And just for convenience, I give you the formulas for the Bayes estimate for beta as well for the variance that we're computing. And remember, in our prior model, we use that the prior mean is equal to 0. So you can go actually back and compare the results that you see on this table with, the results that we got using other prior models. But here you anticipate that these results are really, much better because we use non-informative prior, since the effect of the parameter C has been integrated out. All right, so let me go back to this idea of variable selection. If you remember, we had discussed in the earlier lecture for this null hypothesis where we introduced the constraint R times beta equal to R, where R was a matrix of dimensions Q times K plus 1. So we took that this matrix R has Q independent rows, so it has a row rank equal to Q, which means that Q of the this constraint effectively tells me that I can write Q of the variables beta as a linear combination of the remaining K plus 1 minus Q beta variables. And that way, what I defined is I defined a vector beta 0 that's of dimension K plus 1 minus Q, and then I define a corresponding matrix X0 for this particular constraint. You can go back in the previous lecture to see exactly what this X0 was, but at the end of the day, if you have this hypothesis holding, then you have a new likelihood model that has this matrix X0, and you have a new vector beta 0 that is of dimensionality K plus 1 minus Q. Now, we're going to try to repeat some of those calculations, of course, when C is a random variable with this particular prior. So the prior we're going to use for beta 0 in this new regression problem under this hypothesis H0 is going to look like this. So we're going to take the mean to be 0, and remember my vector beta 0 is of dimensions K plus 1 minus Q, and then we're going to take the prior to have practically the same structure as before, except that instead of X for our generic prior model for beta, now you see we have here X0, right? We have X0, where remember X0 is defined in terms of X and the constraints imposed by this hypothesis H0. And the other thing to observe is when I write this, the constant C here is the same as the one that I use for the full model where all the parameters were included. And also note that the noise sigma square is the same for all of these different types of hypotheses H0 that I can use. Okay? All right. So this marginal distribution of y then under H0 looks like this. Okay? And again, where is this coming? This whole term, except the c minus 1, that is my prior model, this whole thing is the marginal likelihood that we had derived before for the general model where we had 0 constraints. And now what I have done is I took the general model, I changed the dimensionality of my beta variables from k plus 1 to k plus 1 minus q. Okay, and we discussed about this in the earlier lecture. And I changed x to x0, right? Because this is what comes to my likelihood model under the hypothesis H0. So for example, if your hypothesis H0 has this beta 7 and beta 8 equal to 0 constraints, so if this hypothesis forces the 7th and the 8th beta parameters to be equal to 0, you can actually compute the Bayes factor. So this is the log of the alternative hypothesis where these are not 0 versus the H0 hypothesis where beta 7 and beta 8 are equal to 0. This turns out to be minus 0.7884, which obviously favors the hypothesis H0 that beta 7 and beta 8 are equal to 0. Actually, this is not surprising because when we discuss with other type of prior models before, we noticed that the parameters 7 and 8, they were never staying in the model under different type of approaches to this variable selection problem. But now you can see it in this non-informative setting where the parameter C is integrated out. You can come up with similar type of results. So what I'm going to do is I am going to use this particular model where my constraint is going to be a constraint where I'm going to be keeping one variable out of the model. So for example, my hypothesis H0 will be that beta I is equal to 0. And then I'm going to evaluate the Bayes factor beta 10 I, and I put a superscript I to indicate that for each of these calculations, my H0 will correspond to beta I equal to 0. Okay, so I can actually do this type of calculations using a likelihood model that has this form, and then having these prior models that take this particular form. So here are the results for this non-informative G prior. What you see here are again these Bayes estimates for the parameters beta I. These are the variances, and these are these Bayes factors in a log scale. So this is the Bayes factor 10 I, where again I indicates that I remove the beta I from the model one at a time. And you can notice from the values here, the parameters that are shown with stars indicate evidence against H0, which means that literally in this model, the parameter beta 0 is needed, beta 1 is needed, beta 2 is needed, beta 3 we don't need it, beta 4 and beta 5 are needed, even though the argument for them to keep them is weaker than, for example, keeping the intercept in the model. Okay, so let me start moving to Bayesian regression and interface that Bayesian regression problem a little bit more rigorously with the idea of variable selection. So we have k input variables, so k explanatory variables, x1, x2 to xk. And the question we had posed a few times in the lecture today is, do we actually need all of these input variables in our regression problem? Do they need both to explain the data, but also for us to do predictions? So to answer that, let's consider a Q subset of these variables. So I'm going to take the subset to be defined by these indices I1, I2, IQ. So that's a Q subset. Of course, Q greater than equal to 0 and less or equal to k. So if I have this Q subset, I can affiliate with it the following input variables, xi1, xi2, xiq, and you notice I always include the bias term. So when I'm going to try to define a subset of the explanatory variables in my new regression model, I will always keep the bias term, right? So my total number of variables, if you want to include this as a dummy input variable, will be of the order of q plus 1. All right, this is what I have. It's q plus 1. Now, how many models can I have that somehow include, q explanatory variables? If you think about it, that you have k explanatory variables, so each variable can be in the model or can be out of the model. So effectively, the total number of models that you can derive this way is 2 to the power k. All right, and if you think about it, in our case, k is equal to 10, so 2 to the power 10, that's a huge number of models, so that would be prohibiting to actually being able to do evaluations for each of these models and compare which model performs best. So we need to do something about that. So what I'm going to do is first let me write the general structure for x, right? You remember x had a column of 1s, then a column that corresponds to my input variable x1 over all my training data set, and then a column for x2 and a column for xk. So what I'm going to do is I'm going to define the model m gamma, all right, that is affiliated with a binary indicator vector that tells me which variables are in the model and which variables are not in the model. So I'm going to use gamma I equal to 1 when the variable xi is included in the model, and gamma I equal to 0 if it is not. So for example, you can think this gamma vector being, let's say, 0, 1, 0, 0, 0, 0, 0. That means that somehow only the second input variable is being included. Of course, you can have a model that is 1, 1, 0, 1, 1, and the remaining 0. So that means that the first variable, the second, the fourth, and the fifth are being included in the model. But I'm going to index all of these models with this indicator vector gamma that tells me which explanatory variables are in the model. So the total number then of the variables in the model will be nothing else but if I take a unit vector of dimensions k, q of gamma, which defines the total number of variables in the model m gamma, is this vector 1 transpose gamma. Okay? I'm also going to use all the indices of the variables that they are in the model. I'm going to indicate them as T1 of gamma, and the remaining indices that they are not in the model, I'm going to indicate them with T0. So this will give me the explanatory variables that they are in the model, and the explanatory variables that they are not in the model. Now remember, I am going to write down equations for a model gamma that has some variables in the model and some out, okay? But as I indicated, when you look at the parameters beta for the model gamma, you will always incorporate in that model the bias term beta 0. So this will be in every model. And then in addition to that, you're going to keep only the parameters beta I, where the index I belongs to this set T1 of gamma, which again, I remind you, is the set of indices that have the variables that they are in the model. Now I'm going to define also this matrix X gamma to be basically my design matrix X, where I have removed from it, I have removed all the explanatory variables that they are not in the model. Okay, so I have only kept basically my first column of ones, that's the bias term, and the columns basically that correspond to this set T1 of gamma. Okay, obviously we're going to need a likelihood model, which is not very much different from what I had before when we discussed about the hypothesis testing setting. So for the model M gamma, so given gamma, all right, so given that, let's say I know which variables are in the model and which variables are out of the model, my likelihood is a Gaussian with mean x gamma times beta gamma and a noise sigma square. And I remind you this beta gamma is of dimension q gamma plus 1, where q gamma is the total number of variables in the model, and plus 1 to account for the bias term beta 0. All right, now this is the likelihood model for this model M gamma, again indexed by this set gamma. And I want you to pay attention here that this noise sigma square is going to be kept to be the same for all models M gamma. Okay? Otherwise, we're going to get in trouble. So sigma square has to be the same for all models M gamma. The question is now, what are we going to do with the prior models? Right? What are we going to use as a prior for beta gamma? And the right approach to do here is to define a prior model for beta when all the parameters are in the model, so when gamma is equal to 1, 1, 1, 1, all the way for all k explanatory variables, and then somehow, right, define a prior model that is consistent, with this generic prior, global prior model in a certain way. And the question is what that certain way is going to be. So let me just give you all the equations here. This is my general prior model, right? This is my, for a given C, this is my Zellner G prior, right? Beta given sigma square and given C is this. This is my prior mean, and then we took sigma square to follow a Jeffreys improper prior. The question is now, if I'm going to go and use a same structure for the prior for beta gamma, all right? Beta gamma is of dimensions q gamma plus 1. The question is then, what exactly do I use for tilde of beta gamma, and what exactly do I use for x gamma? Right? What exactly do I use for x gamma? And even more importantly, what do I use for C? Because you see here, I'm using the same C. Okay? Now, this is not necessarily a trivial problem. So let me show you two different ways that I can think on actually using this global prior model and restricting it to this local prior model for M gamma. So let me start with the easiest possible way. If you remember, right, I have a set of observations y that using my full model, I approximate them as x times beta. So let me approximate my measurements y as x times the prior mean tilde of beta. So one way you can think in computing this tilde of beta subscript gamma is to minimize the square error between x tilde of beta, and again this is my generic prior mean, and minimize the error from x gamma tilde of beta gamma. Okay, now this problem is a least squares problem. And if you do the calculations, it turns out that tilde of beta gamma is given by x gamma transpose x gamma inverse, x gamma transpose x, tilde of beta hat, okay? I'm sorry, tilde of beta. And we don't have any problem with x gamma because I remind you x gamma is the design matrix where I keep the first column of ones and I only keep the columns for the explanatory variables that have gamma equal to 1, right? The rest are not there. So this equation, right, using this solution of this least squares problem can define what the prior of my restricted model M gamma is going to look like. And there is another derivation that somehow gives you the same result, and I'm only going to highlight it. The proof is in the bottom of this slide. So in principle, right, what we have here is we're splitting this vector beta for the full model to a vector beta gamma that corresponds to the inputs that have gamma equal to 1, and then including, of course, the bias term, and then the remaining beta variables that I indicate here as beta minus gamma. So one way to actually think of computing this prior mean for the restrictive model is to actually think of this as a conditional Gaussian model. So let me do it as follows. The joint distribution of beta gamma and beta minus gamma is actually my full prior model that you see on the top. So the question is, using this full model, can you actually derive the conditional distribution of beta gamma given beta minus gamma? And the answer is, if you follow the algebra, right, and you do use the partition of this covariance matrix using a partition of the precision matrix, it turns out that you actually do get exactly the same answer as solving this least squares problem. I understand that none of these two approaches may be satisfactory in a rigorous mathematical way, but somehow the key message here is we are using a global model, prior model for beta given sigma square, and then we restrict this model by either this least squares approach or this conditional Gaussian approach. So that way the prior mean for model gamma is derived actually directly from this tilde of beta, which is the prior mean for the global model. So if I knew gamma, right? If I knew gamma, what I can do is I can, I'm introducing a joint prior that looks like this. All right. So that's my prior mean for model gamma, and again, this term and everything else comes from the Gaussian of beta gamma given sigma square, and this other minus 1 there comes from the prior on sigma square. All right, so now we are going to compute a posterior over models, and to compute a posterior over models we're going to need a prior over models, and the prior over models we're going to take a uniform prior. You remember we said there's a total of 2 to the k models, so the appropriate uninformative prior for gamma will be 1 over 2 to the power k. All right, so we're going to have way too many models, all right, but we're going to try to compute the posterior distribution of gamma, which in essence will be the posterior distribution over models. All right, so let's see how somebody can compute the posterior over models. All right, so this is what is of interest to us, the posterior over models. That's the marginal likelihood over models, and I call it marginal likelihood because you notice there is no beta or sigma square anywhere here, times the prior over models, which we took it to uniform, so this disappears. So it turns out that the posterior over models is actually the same as the marginal likelihood. And you remember, if we know what gamma is, we know what the marginal likelihood is, right? So we had before derived equations for the full model. So if you go to that full model and you substitute x with x gamma, if you substitute the prior mean tilde of beta with tilde of beta with subscript gamma, then you will actually be able to write down an explicit expression for this marginal likelihood given gamma. And if you want the expression analytically, this is basically the likelihood where if you knew gamma, if you knew the parameters, times again the prior given gamma. So this is really the prior for that gamma model, And then, of course, we have a prior on sigma squared that we take it to be the same for all models. So the somehow in the calculations that I had in the earlier lecture, we had derived this conditional likelihood given sigma square. So if I knew gamma, right, and I knew sigma square, I can use my generic formulas that I had before. And actually, I notice here I should have so given gamma, all right, I should put here a beta gamma, okay, a beta gamma. That's an omission, but somehow, right? Somehow I can write this marginal likelihood given sigma square and given gamma. I can cut and paste the formulas that I had from before, all right, and this is what I get. So this is for effectively for model m gamma given sigma square. This is the marginal likelihood. Now, of course, what we will need to do now is to derive this. We're going to need to integrate sigma square out, okay? And the prior on sigma square is this Jeffreys prior 1 over sigma square. And if you do all of this, here is the final formula. So what you see here is the marginal likelihood, which is proportional to the posterior of gamma. You remember that, right? So the posterior of gamma is proportional to the marginal likelihood, okay? And that's my final result. And it looks identical to the marginal likelihood formula that we had in the earlier lecture, where instead of x, I have x gamma, and instead of tilde of beta, so the prior global mean, I have the tilde of beta with subscript gamma, which is the consistent prior mean for my model m gamma. Okay? You don't actually need to worry about the way that I derive this tilde of beta gamma, because in the results that I'm going to show you, I am going to take the tilde of beta is equal to 0, and then all of this tilde of beta for all models gamma, they will also be 0, so the calculation that way will be simplified. But remember, this calculation that you see here is for a given parameter c, okay? I know before we integrated c out to get a fully uniformative limit, so this calculation is for a given c, so I will be better off, for example, to put a comma c here, but hopefully by looking on the right hand side you appreciate that this calculation is for a given c. Alright, so, and by the way, this is cut and paste the general formula that I had for this marginal likelihood for a given c from our earlier lecture. So effectively you can appreciate that this formula here, it's identical, it is the same formula, just changing x to x gamma and just changing tilde of beta to tilde of beta with subscript gamma. Alright, so we have the posterior over models that is proportional to this marginal likelihood. So what I can do is I can take these 2 to the power 10 models that I have, and I can actually exhaust and go through all the possible calculations and can compute this posterior of gamma. So this is what you see in this table. I am fixing c to be 100, I am taking the prior mean to be 0, and this is a part of the calculations of these posteriors for different models, and I have ordered these models in an order starting with the highest posterior model, right? That's the model that has the bias term, the explanatory variables 1, 2, 4, and 5, and the second highest posterior model is the one with variables 0, 1, 2, 4, 5, and 9. Okay? Obviously, these particular variables 1, 2, 4, and 5 for the caterpillar problem, they have a specific meaning, but we're really not interested. But in a practical situation, that may have a lot to add to your overall analysis of the regression problem. Okay, Now, can we go one further step, right? So we derive this posterior over models, but we did this for a given C. Can we actually make this fully an informed model by integrating with C? Okay, and the answer is yes. I can multiply this by what I had before with the prior of C, which is 1 over C, and integrate over all possible integer values of C. This is what I had before, and again, I have dropped tilde of beta and all the tilde of beta with subscript gamma, so that's why none of them comes here. So that's the posterior, right? That's the posterior over models where C has been integrated out, okay? So this is the Zellner's non-informative prior basically is being used in this analysis, okay? And again, remember the posterior of gamma is basically proportional to the marginal likelihood, and the marginal likelihood we had computed it for a given C times the prior. That's the formula, which is the same as what we have here. The only difference is for model M gamma, I am writing X gamma instead of X, and I am writing, there's no beta, tilde of beta here, so I don't have to worry about that. Okay, so if you take this Zellner's uninformed prior, so there's no C anymore, and you compute the, you go through all potential 2 to the power 10 models, and you compute the, let's say, the highest ranking in terms of posterior models. Again, 0, 1, 2, 5, 4, 5 has the highest posterior probability. So this, again, these calculations are done using the non-informative G prior, all right? So they are more reliable if you don't have any sensible prior information, so they are more reliable from the table that I showed you before, where we use a particular C, if I recall, C equal to 100. Okay, now generally trying to have an exhausting list of these models, which is 2 to the power k, right? K is the number of explanatory variables. That's a very difficult task, and so you will not be able to do this. If k is 1,000,000 or 1,000, you know, having 2 to 1,000,000 or 2 to 1,000, it's a huge number of models. It will not be realistic to do variable selection. So we're looking for using Monte Carlo methods to do that. And that's how we're going to finish the lecture today, by bringing together everything we learned about Gibbs sampling with this variable selection in the context of Bayesian regression models. All right, so obviously we are going to play with this posterior of gamma, right? This is what we're going to do. And if you remember, to be able to do Gibbs sampling, you need to have an access to the conditional posteriors. And the conditional posteriors, I'm writing them here. So if you define gamma minus I to be all the gamma parameters except the parameter I, the conditional posterior of gamma I, given all the other variables, is given like that. And you can appreciate, right, that this is basically proportional to the posterior of gamma. All right, so the this conditional distribution of gamma I is proportional to the posterior of gamma. And remember that each of these variables gamma I can only take values 0 and 1. Okay, so Gibbs sampling actually cannot be that difficult. So let's see how we can actually implement Gibbs sampling. So if I just cut and paste the generic algorithm, right, you can think of it as you sample, let's say if you do this a systematic ordering, and you start updating gamma 1, then gamma 2, then gamma k, you're going to have to update gamma 1 by sampling from this conditional posterior distribution, where you keep all the other gammas fixed. So all the other variables, they are in or out in the model depending on what values you have currently, and then you will decide if gamma 1 is in the model or not. Then once gamma 1 is fixed, you will decide about gamma 2, and then eventually about gamma k, where all the other gammas are fixed to whatever you decided on the earlier k minus 1 steps of the Gibbs sampling algorithm. So let me concentrate on sampling from in one step. How do we sample from the conditional of gamma 1 given all the other gammas? All right. So I mentioned before that these conditional posteriors are basically proportional to the posterior of the whole of gamma. Okay, and I'm writing here. This posterior of gamma 1 given all the other gammas, right, is proportional to the posterior of gamma 1, gamma 2, gamma k, etc., where obviously all the other variables are fixed to whatever values they are. And the value for gamma 1 can be either 0 or can be 1. So effectively what you need to do is you need to take this posterior that we computed analytically a few slides ago and then evaluate it for gamma 1 equal to 0 and gamma 1 equal to 1. So if we call these probabilities P0 and P1, you can immediately see that with probability P0, gamma 1 equal to 0, and then with probability P1, gamma 1 equal to 1. Okay, so it is very simple then to implement and sample from this conditional, of gamma 1 given all the other gammas. Okay, and again, the only thing you have to do is calculate the posterior of gamma using the values gamma 1 equal to 0 and gamma 1 equal to 1 and keeping all the other gammas at whatever previous values you have already evaluated. And of course you can do the same thing for the conditional of gamma 2 and gamma 3, etc. Alright, so you have a way now to explore the posterior of gamma. And in that way then, if you ask yourself, so imagine that at each iteration of the Gibbs sampling, right, you have samples of this vector of gamma 1, gamma 2, gamma k that tells you which variables are in the model and which variables are not in the model. So if you want the posterior of a particular model, so for a particular vector, let's say the vector gamma, maybe you include certain variables, not other variables. So if you're looking for the posterior of gamma, then effectively you have to see how many of your samples the gamma t was equal to gamma. So by summing all of these indicator functions and averaging, that's your Monte Carlo estimate, that will give you the posterior of gamma. Now I have to mention here, right, t is the number of Markov chain Monte Carlo iterations that you do, and T0 here is the burn-in periods where effectively your samples are not very reliable, they're not samples from the target distribution, so you basically start doing this Monte Carlo averaging after T0 burn-in steps, okay? So the first T0 steps, you don't use those samples, but after that you can average, and this will give you this posterior, an estimate of the posterior of gamma. These estimates here, following our standard notation, I indicate them as pi hat. So when you see pi hat, immediately you know that is an estimate of that distribution of the posterior, in this case, evaluated with Gibbs sampling. So here are the results, all right? I am first using them for a given C, all right? So this C is 100 and tilde of beta is equal to 0, and all the remaining tilde of beta with subscript gamma, of course, will all be 0. This column comes from the exhausting calculation of this posterior for all models, okay? And this is what you get using Gibbs estimate. And you see the calculation, the exact calculation more or less agrees very well, all right, to the third decimal digit, if you like, with what you get with Gibbs sampling. So this is very nice. If you now integrate C out and you use the non-informative G prior, you can actually, again, we have the same table, all right? It gives us, this is by evaluating the posterior at all possible models, and this is by taking the top ranking models that we evaluate using Gibbs sampling, and you can see the results agree quite well. Okay, so Gibbs sampling is capable to actually provide us what is the highest probability model, and the highest probability model tends to be the one that includes the bias term and then the explanatory variables 1, 2, 4, and 5. So actually both the analytical and the Gibbs sampling estimates agree for practically all of the top posterior models that we have in our analysis. Now you may ask also questions, what is the probability that a particular explanatory variable gamma I is in the model, any model? And so you can ask what is the probability that gamma I equal to 1, and effectively, after a burn-in period of t0, what you can do is take all your samples, look at all realizations of gamma, and see for which ones gamma I is equal to 1, and then take a Monte Carlo average, and that will give you actually the probability of inclusion of a particular variable in the model. And here is what you actually see here, and you see a comparison of these inclusion probabilities, where the first column, so this is for all variables from 1 to 10, and so the first column is computed for an informative model with tilde beta equal to 0 and c equal to 100, and the second column is computed for the fully non-informative G prior model, where C again has been integrated out, and obviously these results are more reliable if you don't have any prior knowledge on C, and they eliminate any worries that you may have by using a specific value for C. There's no C coming here, so these are the results that I will actually advocate for using in your analysis. All right. So these last two lectures have been very lengthy, very time consuming, but I hope you will be able to appreciate on how Monte Carlo methods can come together with Bayesian analysis to address this variable selection problem in a Bayesian regression analysis. Now, we restricted ourselves to a very particular type of prior models in our analysis, but literally whatever we have discussed today, you can use it in any other setting for regression models using another prior model, maybe another likelihood model. I believe still you should be able to do the same type of variable selection as what has been highlighted today, both analytically but also with Monte Carlo methods. All right, that's the end of the lecture today. Happy readings, and I will see you in 2 days with a follow-up lecture on Monte Carlo methods. Bye.